Hi! Today's lesson is about how we can visualize the bonds that we learned about last class. Friendly reminder that we learned there are three types of bonds holding atoms together: metallic, ionic, and covalent. You will never be asked to visually represent a metallic bond because to try to draw on paper that sea of mobile electrons is quite difficult to do. So the focus of our lesson today is going to be on how we visualize bonds that are ionic and covalent. Whenever you're asked to visualize bonds, ultimately, the main goal is to show what's happening to the valence electrons. Because remember, the valence electrons are the only ones involved in bonding. The core electrons are not. A reminder from last class, from last lesson, in an ionic bond, the valence electrons are lost from a metal and gained by a nonmetal. We need to show that losing and gaining. That's what we mean by visualizing bonds. And in a covalent bond, we have to show that the valence electrons are shared between atoms of nonmetals. Thinking back to the atomic structure unit, we learned about the electron configuration dot notation, where we were showing the valence electrons of an atom. As we visualize these ionic and covalent bonds, we are going to use Lewis dot notations. Lewis dot notations. They are not the same thing as the electron configuration dot notation. To remind you, the electron configuration dot notation, the purpose of that was to show what was happening, the electrons in the orbitals. So for example, if we had an electron configuration that ended something S2, something P2, those two electrons in the S were paired up, and the two electrons in the P were not paired up. So the dot notation for this would look like two dots paired up, and then two dots for the electrons that are singly placed in the P orbitals. The Lewis dot notations, their purpose is to show bonding sites. And since it has a different objective, the Lewis dot notations are going to look slightly different from the electron configuration dot notations. Let's go through one group at a time what the dot notations will look like. The elements in group 1 have one valence electron. Therefore, they will have one dot next to their symbol. And I'm going to use the symbol X because I could mean hydrogen or potassium or francium. Any of those elements from group 1, they will have one dot next to their symbol because they have one valence electron. My elements in group 2, they have two valence electrons. Again, they're going to have two dots, but unlike what we did in the electron configuration dot notation, I am not going to pair the dots up. I'm not showing what it's like in the orbitals but rather I'm trying to show the electrons that can be lost and gained, henceforth can form bonds or shared. The elements in group 13 have 3 valence electrons. They are going to have 3 dots around them, and they're going to be separated out. So just like with electron configuration dot notation, imagine that the orbitals, are forming a box around the symbol of the elements. So we still have these elemental symbols in a box, an imaginary box, and we're still putting 1 dot or 1 electron on each side of the box. The elements in the carbon group, or group 14, have 4 valence electrons. Therefore, they will have 4 dots around their symbol, each imaginary side of the box getting 1 dot. The elements in the nitrogen group, which are group 15, they have 5 valence electrons. If I follow the pattern that I've been doing here, we have 4 sides to our imaginary box, but 5 electrons that I need to organize. So I'm now going to need to choose a side and double up on it. The elements in the oxygen group, or group 16, have 6 valence electrons and therefore are going to need 6 dots around their elemental symbol. Remember, each dot represents a valence electron. 4 sides to the box, and then the remaining 2 have to get doubled up on 2 sides of the box. It doesn't matter what sides they're on. It just matters that the elements in group 16 have 2 sets of paired electrons and 2 lone electrons. Our halogens in group 17 have 7 valence electrons. They will have 7 dots around their symbol. Again, it doesn't really matter where the doubling up and the singling go. It's important that group 17 elements have 1 dot by itself. And finally, my elements in group 18, all of them except for helium, are going to have 8 electrons around them. So theirs is going to look just like the electron configuration dot notation, or we have helium with the 2 dots. Again, what is it that we're trying to show? We're trying to show bonding sites. Bonds can form where there are lone electrons. And by lone electrons, we mean they're not paired up. All right, so let's jump into an example. What if I wanted to show a bond that forms between a sodium and a chlorine atom? Well, first things first, sodium is a metal, chlorine is a nonmetal. I know that an ionic bond is going to be responsible for holding these particles together. So I now need to start to show this transfer of electrons, right? We said here an ionic bond is that electrons are lost from a metal and they're gained by a nonmetal. I need to start to show that. How do I start? Well, I'm going to go with those original puzzle pieces. Sodium is a group 1 element. It is going to have 1 dot in its Lewis dot structure. Chlorine is a halogen in group 17. It is going to have 7 dots in its Lewis dot structure. These are like the original atoms. Original atoms, which I call puzzle pieces. That's really not like a chemistry thing. It's a me thing. The original atoms, or the puzzle pieces, because that's what we're starting with. And what I'll need to do now is I'm going to have to show the loss and gain of electrons. And remember, these dot diagrams only show the valence electrons. The metal sodium, because it has a low ionization energy and a low electronegativity, it's going to want to lose its valence electrons. The nonmetal chlorine, on the other hand, has a high electronegativity. It's really good at gaining electrons, and it has a high ionization energy. It takes too much energy to remove its electrons. So I literally show the loss and gain using an arrow. I'm showing the electron from the metal, how it's going to move from that spot and be accepted by the chlorine. Now, what we wind up having are ions. And therefore, I need to show the resulting ions. In other words, now that the sodium atom has lost its electron, it has no more valence electrons in the third energy level. Therefore, I will not draw any dots around its symbol. However, I will indicate that it's now a cation with a charge of +1, and I will put that symbol in brackets. The chlorine atom just gained an electron from the sodium, and it now has 8 electrons around its symbol. I will indicate that it has a -1 charge because it has gained 1 electron, and I will put its symbol in brackets. And this whole thing I'm circling right now, from the original puzzle pieces to the arrow that's showing the metal losing its electron and the nonmetal gaining it, and the resulting ions in the bracket, that whole thing all together is my final answer. That's how I visualize an ionic bond. I'm showing what's happening to the valence electrons, and then ultimately the electrostatic attraction between the cation and the anion. Let's try another example. Let's try an example that shows the bond that forms between magnesium and bromine atoms. Again, we've got a metal with a nonmetal, so I know I have an ionic bond. I need to show the loss and gain of electrons. I do that by starting with the original Lewis dot structures. Magnesium is a group 2 metal, so its Lewis dot structure has 2 dots that are not paired up. Bromine is a halogen in group 17. It will have 7 valence electrons around its symbol. I need to show that the magnesium is going to lose its electrons to the bromine. Well, bromine only has 1 lone electron. In other words, it's only got 1 spot open where it can gain an electron. So by stealing or taking one of the magnesium's valence electrons, that bromine atom is now stable with a full shell. It has achieved its goal. Looking at the magnesium atom, though, it has not achieved its goal yet. It still has 1 valence electron, and it doesn't want that. It wants a full shell. It still wants to lose that electron. Well, given the atoms that we have, the only way that we can make the magnesium stable would be to add another puzzle piece or another atom that can gain that second electron from magnesium. In other words, I need another non-metallic atom to gain. And I can't just pick a random one because I'm telling you that this compound is made up of magnesium and bromine atoms. So I have to add another bromine atom. By doing so, I'm now able to show that that second valence electron of magnesium can now be gained by that second bromine atom we just added. Now, the magnesium atom is satisfied, it's stable, it has lost both of its valence electrons, and that second bromine atom is stable. It has gained 1 electron to have a full shell. The resulting ions. Magnesium has lost 2 of its electrons. Therefore, it has no more valence electrons. So I draw no dots. I indicate that it is a cation. It has a 2+ charge, and I put it in brackets. The bromine puzzle piece. It has gained an electron. So I will now draw 8 valence electrons, or 8 dots around it. The bromine puzzle piece, because it's gained an electron, now has a -1 charge. I will put that in brackets, but the only way that that worked was if I had 2 bromine atoms. So I will then put a 2 outside of the brackets as a coefficient. And ultimately what that means is that for every 1 magnesium, we'll have 2 bromines that are attracted to it. Right? Remember those crystal lattices we were looking at yesterday? So it's this conglomerate where your ratio is going to be 1 magnesium for every 2 bromines, but they're still going to all be attracted to each other in this crystal lattice formation. All right, let's try one more. What if I were going to have a compound formed between lithium and oxygen? Lithium is a metal, oxygen is a nonmetal, so I'm visualizing an ionic bond. I need to show the loss and gain of electrons. Lithium is a group 1 element. It has 1 dot around its symbol. Oxygen is in group 16. It has 6 valence electrons around its symbol. I'm now going to show the loss of the electron by the metal and the gaining of the electron by the nonmetal. The lithium atom is happy now because it has no more valence electrons. Its core electron shell is now full. However, the oxygen atom is not yet stable. It still has 1 more electron that is not paired up. And we know that every atom needs to have that stability of a full valence shell. What must I add? I must add another lithium atom, because in this particular compound, it's the lithium atoms that will be losing the electrons. By adding another lithium atom, the oxygen is now able to gain its valence electron. The oxygen atom is now satisfied because it has gained a total of 2 electrons. And that second lithium atom is satisfied, it's stable because it has lost its 1 valence electron. The resulting ions, lithium has no more dots around it, it's lost its valence electrons. It has a +1 charge, and I will put it in brackets. That's what we do for ions. And I needed 2 of them in order for the oxygen atom to be stabilized. And speaking of the oxygen atom, it now has 8 electrons around it. And it gained 2 electrons, so it's a 2- charge. And I put that symbol in brackets as well. So again, my final answer, like when you are confronted with the task of visualize the bond that forms between these atoms. For an ionic bond, you have to show all this work. Let's move on to another example, and we'll switch it up. When we get to the situation where we have 2 nonmetals, you're always going to need to be told what the formula is, because there are a variety of different combinations that can result when these atoms of the nonmetals bond with each other. So again, I've got 2 nonmetals, so I know I'm going to be a covalent bond. The covalent bond needs to show the sharing of electrons. Let's start with those puzzle pieces. Hydrogen is in group 1, it has 1 valence electron. Oxygen is in group 16, it has 6 valence electrons. Now my formula automatically tells me that I'm going to need 2 hydrogen atoms in order for the oxygen atom, the 1 oxygen atom, to be stabilized. When you're working with covalent bonds, the reason why I used that term puzzle pieces before is because we're literally going to like click the Lewis dot structures together as if they were pieces of a jigsaw puzzle. And they're able to be clicked together at the lone electron locations. In other words, hydrogen needs 1 more electron in order to have a full shell. Remember, energy level 1 can hold a maximum of 2 electrons. The oxygen atom needs to have access to 2 electrons in order for it to have a full shell. So if I were to take this hydrogen atom, where it has 1 lone electron, and pair it or click it up with where the oxygen's puzzle piece has 1 electron, these are now shared electrons. And because they're shared, the hydrogen and oxygen atom both have access to it. So the hydrogen is now stable, it has a full shell, and the oxygen atom is almost stable. It still has 1 more electron that's alone. So if I take this second hydrogen atom and slide that one or click it into the spot where oxygen's lone electron is, and those ones are again shared, that's where we have our covalent bonds. Now let me clean this up a little bit, because it looks like things are overlapping. What we wound up doing was clicking these pieces together, excuse me, in this fashion, so that our atoms aligned like so. With the covalent bond, that is the final answer you'll have to represent. You don't need to show all of your work in terms of the original puzzle pieces and how they're clicking together. You can just show what the final puzzle looks like after the pieces click together. When we have 2 shared electrons, that is called a single covalent bond. And we kind of dropped the word covalent. We just call it a single bond, we being chemists. So what we mean to say is that the hydrogen and oxygen atoms are held together with a single bond, a single covalent bond, because they're sharing 2 electrons between those atoms. That can then be translated into the ball and stick model, where I can take those oxygen, wherever there's a shared electron, I can change that into a dash. And I'm still going to show the lone electrons on the oxygen. So for every 2 shared electrons, you can replace the dots with a dash. And every time you see that dash, you automatically know that means a single bond, and you know that 2 electrons are being shared. In last lesson, we learned that there are 2 types of covalent bond, polar and nonpolar. By subtracting the electronegativities, we knew that the bond between hydrogen and oxygen is polar. And visually, I hope you're able to see that as well. See how the oxygen atom has these extra electrons on it? That's because it has a high electronegativity, plus it has more valence electrons. It's going to be better able to gain electrons than the hydrogen atom. So what's really happening is the electrons are being pulled more often to the oxygen atom. And we indicate that with an arrow, showing where the electrons are going. And on the tail end of the arrow, we put a little like hash mark. When you break that apart or like circle it, see how it's like a plus sign? That means that this is a partial positive. Now that funky thing that was partial, that's a lowercase Greek letter delta. That means partial positive charge. It's not a full charge like an ionic. The oxygen did not totally steal or remove the electron from the hydrogen atom. It is sharing. However, the oxygen atom, since it has a greater electronegativity, is going to have access to those electrons more of the time. And therefore, the oxygen end is going to be referred to as partial negative. Again, that's a lowercase Greek letter delta, and it means partial. That's what the lowercase Greek letter means, partial negative charge. That's where more of the electrons are hanging out more of the time. And my other hydrogen atom here will be that partial positive. And you could only do that for polar covalent bonds because that's the unequal sharing of electrons. And we're showing within our diagram where the bonds are happening and then which atom, if any, is hogging the electrons for more of the time. Let's try another one. What if I wanted to do carbon and fluorine, where the formula is CF4? Two nonmetals, so I know I'm going to do a covalent bond. Covalent bond means sharing. Start with the original puzzle pieces. Carbon has 4 valence electrons. Fluorine has 7. According to the formula, I'm going to need 4 of them. This brings us to a guideline. We're always going to start with the puzzle piece that has the most number of bonding sites. Start with the puzzle piece that has the most number of bonding sites. One more time. We're going to start with the puzzle piece that has the most number of bonding sites. That's going to be the one that goes in the middle. In other words, that's the one that we're going to connect others to. We're going to connect the other pieces to it. And we did that in our first example, right? We started with the oxygen and clicked the 2 hydrogen atoms into it. It was much easier to see when you have fewer atoms. But here we have 5 total atoms, and for a lot of times, especially as beginners, it's like, where do I start? You start with the puzzle piece that has the most number of bonding sites. The carbon puzzle piece has 4 lone electrons, so that's 4 bonding sites. The fluorine puzzle piece has more electrons than the carbon, but only 1 bonding site. So I'm going to start with the carbons. The carbon puzzle piece is going to be the one that goes in the middle, and I'm going to wind up connecting the other pieces to it. For a lot of people, once you get that starting puzzle piece, now you can easily see how the fluorine puzzle piece here, I'm going to take its lone electron, click it in, and jot down the other ones. Now I might have to sort of like, I don't know if I can do this, but like rotate, right? I can't. But if I were able to like rotate this clockwise, you could better see how that piece would fit in here. So wherever that lone electron is, because remember, it doesn't really matter where you put the electrons around the symbol. but now the remaining 6 are all paired up. That third fluorine puzzle piece, that lone electron will click in to where carbon has a lone electron, and then the remaining 6 electrons around fluorine will just get shifted. And that last fluorine puzzle piece will repeat the same pattern. Where the fluorine's dot is alone, that's now going to click into where carbon's lone electron is, and the remaining 6 are going to go around it. Another way you could choose to write this is with those dashes coming off the carbon. You still need to draw all the other remaining valence electrons around the fluorine atoms, but you can certainly change those 2 dots into a dash. The last thing we need to do is check our polarity. Carbon's value for the electronegativity is 2.5. Carbon is 2.5. Fluorine is 4.0. When I subtract them, I get a difference of 1.5, which is polar covalent. In other words, my fluorine atom is hogging the electrons. How do I show that? Well, I show it with an arrow that points from the carbon to the fluorine, and I put a little hash mark at the opposite end of the arrow. And I'm going to do that for every bond. That means my fluorines are partially negative. They're hogging the negatively charged electrons more of the time. And in the center, my carbon is partially positive. Let's try another example. Let's try a diatomic element, oxygen. Oxygen is in group 16. Each piece will have 6 valence electrons or 6 dots around it. Some of you, now that you're able to start to anticipate, oh, I've got 2 nonmetals, I know it's going to be covalent, I know I need to show my sharing. When you draw your puzzle pieces, you may already start to set yourself up for that clicking in of the puzzle pieces. These 2 oxygen atoms each need access to 2, right? So if I take them in this fashion and I move them and click them in, I now have this situation where I've got 2 shared electrons between the oxygen atoms. However, they still have 2 electrons that are not paired up. According to the formula, I cannot add any more atoms like we did with the ionics. In covalence, that doesn't happen. I have to work with these 2 puzzle pieces only and the number of valence electrons that they have together only. I cannot add puzzle pieces to the covalence. So what can I do to make both of these atoms stable with full shells? Well, if I had the ability, I would click these 2 together again. And as a result, there would wind up being 4 shared electrons between the oxygen atoms. That is a viable occurrence, and it's referred to as a double bond. A double bond is where we have 4 shared electrons. If a single bond is 2 shared electrons and we have 2 sets, hence a double bond. Perhaps for some of you it's easier if we change those shared electrons to the dashes and you're able to see this double bond. Oh, you keep moving the electrons around the oxygen. That's okay. That is totally fine. What I'm keeping is that each of those oxygen puzzle pieces have 4 electrons of their own and 2 shared. Totally fine. There can be one more occurrence, and this will be the last example that we do for today. What if I wanted to show 2 nitrogen atoms bonding together, because nitrogen is another one of our 7 diatomic elements. Nitrogen is in group 15, therefore has 5 valence electrons. 2 nonmetals, valence electrons are going to be shared. Want to show them start to click together. Again, for a lot of you, that first click is an easy one to see. But where we start to struggle is recognizing that nitrogen still has, each of them has 2 electrons that are still alone. So if you remember what we did with the oxygen, we said, all right, what if I were to click together this next set of lone paired electrons? So I would wind up having 4 shared electrons around the nitrogens. Aha, that's a start. We're still getting closer to stability. This nitrogen on the left has access to 1, 2, 3, 4, 5, 6, 7 electrons. And the oxygen on the nitrogen, on the right has access to 1, 2, 3, 4, 5, 6, 7 electrons as well. So we're almost at that stable state of having access to 8 electrons. How can we go about making both of these atoms stable? Well, we've still got these electrons that are alone. If we could click them up again and wind up having a total of 6 shared electrons between those nitrogen atoms, now the nitrogen on the left has access to 8, the nitrogen on the right has access to 8. They both have full shells. This is called a triple bond. And that's where 6 shared electrons exist. To clean it up, for every 2 electrons, we draw a dash. So if there are 6 shared electrons, we'll show 3 dashes. Henceforth, the triple bond. So now that you have the basics of how we visually show ionic and covalent bonds, take a shot at trying it for yourself in the independent worksheet. And remember, in those instances in the compounds where we have both ionic and covalent bonds existing, that you're going to have to show both. You're going to have to show which atoms in that compound are sharing electrons, and then where is the electron transfer happening. It's great stuff.